Hello everyone, welcome back to the How series. We are beginning session 8 of the workshop Programming and Optimization for Intel Architecture. Session 8 continues the module on performance optimization, and today we are going to discuss common problems encountered in multi-threaded applications. This session builds on the material of session 4. So if you're watching this as a recording, maybe it's a good idea to revisit session 4 if you're not familiar with this material. You can watch all of the recordings on the course web page. This is the URL. Also on that page you can download the slides of my presentations, code for all of the exercises, and if you're watching this presentation live, you can also participate in the chat. The chat is on the course web page at the very bottom, and as I speak you can ask questions and we will follow up as we go. If your questions require an extended answer, you can ask them on our forums. You can navigate to the forums from the main menu or using this URL. This is a hands-on workshop, so make sure you take advantage of the opportunity that comes with it. You can practice all of the exercises on a cluster equipped with Intel Xeon processors, multi-core architecture, and Intel Xeon Phi coprocessors and processors, which is many-core architecture. You can use the compute nodes of the cluster at any time during the 2 weeks of the workshop. As usual, I like to remind you that when we talk about performance optimization, we are trying to learn portable techniques so that the code that you write in C, C++, or Fortran can be recompiled and reused on multi-core processors as well as many-core over the memory address space of the encompassing process. And the idea of threads is to run different threads on different cores. This is how you can take advantage of the multi-core or many-core architecture. In OpenMP, your program begins in the initial thread. So initially your program is sequential or serial. At some point you will have a directive, pragma OMP parallel, sometimes combined with other directives. It creates threads, and if you have for loops inside, you can also use directives to do work sharing. So multiple threads exist in this region, and the entire code in the scope of pragma OMP parallel is executed by every thread. At the end of this parallel region, the threads are joined, and you continue in the initial thread. It is easy to make your program multi-threaded, but it may not be easy to make it at the same time efficient and correct. And we are going to talk about common issues found in multi-threaded applications. I will discuss excessive synchronization. Let's just call it too much synchronization, a common issue. Another common issue that people encounter is false sharing. And I will talk about what it is and how to eliminate it. Insufficient parallelism. Your application may be parallel, but not parallel enough to take advantage of the platform that you're working with. I will talk about resolving it and finding parallelism in your applications. And I will also talk about load and balance, another common issue in multi-threaded applications. For each of these topics, we are going to have a hands-on exercise. And today, I will explain the theory and then follow up with the exercise. So let's talk about having too much synchronization. What we're going to talk about will remind you what we did in session 4 when we optimized the integral calculation. Essentially, it boils down to not using murexes too often. And we will once again discuss the reduction pattern. Only this time, our problem will be a little bit more complicated. For the example problem, we will use binning. And we actually started talking about the binning problem yesterday. What we did is we took the naive code, and with the help of strip mining, we vectorized this code. To remind everyone, the problem that we are solving is this. We have a large array containing floating point numbers from 0 to 100. These numbers are ages of different people. We are studying an array of 100 million ages. So basically a large array, enough parallelism. Our goal is to compute how many people are in the age group 0 to 20 years, how many people in the age group 20 to 40 years, 40 to 60, and so on. A total of 5 age groups. So M is equal to 5. To do that, I take each person's age divided by the group width, which is 20 years. This is the group width. When I do this, I get a number. I have to round this number down to an integer, and it gives me the age group number. For example, somebody 56.8 years old maps to age group number 2, which is this age group. And then I use this index 2 to increment the histogram counter, like this. Well, it was not trivial to definitely there's parallelism, because if I can do this calculation for one person, I can do it in parallel for many people. But the difficulty was that this is parallelizable, but that is not, well, at least it's not vectorizable unless you're using a Knight's Landing processor. So what we did yesterday is we split the loop into two. One loop only does vectorizable calculations, and it is going to be auto-vectorized by the compiler. The other loop is not vectorizable. It has conflicts. On Xeon Phi second generation, it will be vectorized because it has the conflict detection instruction. On all other platforms that we have access to, no vectorization. But this is the nature of the application. In order to reduce the pressure on memory, in addition to splitting the loops, we did strip mining. When we strip mine the loops, the outer loop goes through all ages, but with a stride of 16. And then the inner loops only have a length of 16, and they iterate over 16 ages. This is done so that this array index is small. We need this array to compute indices in one array, and then to use them in, to compute indices in one loop, and then to use them in another loop. We want it to be short to minimize pressure on the memory subsystem. This is why we did strip mining. I will take the code where we left off, because what we saw is that, well, what we did is good for performance, but still there's a huge gap between the CPU performance and the Xeon Phi performance. That's because there's no multi-threading, and more work is needed to take advantage of multiple cores. So I will pick up where we left off, and we will implement parallelism in this thread parallelism in this calculation. Let's just do it in the code. So we were working in House Series Labs 4404, and we were editing the file worker.cc. Let me also do this in my other window And this is the code that we were left with yesterday. Okay, so if we are processing one large array at a time, where is the opportunity for thread parallelism? In this code, it's trivial. Well, this loop only has 16 iterations, and it is already parallelized, so this is in fact one vector operation. So there's no more room for parallelism. And the only other loop left as a candidate for parallelism is this one. Can we parallelize it? Let's think about it. I can put pragma OMP parallel 4. This is a familiar construct from session 4. And then different values of II will go to different threads. So each thread is going to access array H, but different elements of it, and store it in the temporary array J. Well, it was called index in my slides, now it's J. And then it's going to write into the histogram. Looks like there's two possible data races. This is a possible data race, and this is a possible data race. With J, it's easy to resolve because J is just a temporary array. So I can do private J, and the compiler should replicate this array across all threads. Okay, so now this is no longer a data race, but that is a data race. So what do we do with it? It may be tempting to protect it with a mutex because, well, the value of J is going to range from 0 to 4. So with 256 threads, definitely multiple threads will be writing to the same value of J. But all they do is incrementing it, and this is an atomic operation. In fact, we have tried something like that in session 4. I know that it's not going to work, but I'm tempted to try anyway, because, well, maybe this time we have more of parallel code to compensate for the overhead of the synchronization. So I'm recompiling and rerunning. As you can see, a compilation occurs for the CPU, for a Knights Corner coprocessor, and for a Knights Landing processor. Looks like the code is still running. Well, what performance did we get last time? Performance is measured in values processed per second. So let's see what we get now. So we inserted parallel 4 to get the code to run in parallel, and then we inserted pragma OMP atomic to resolve a data race. So it finished on the CPU. And we are getting 4.0 times 10 to 7. So instead of accelerating our code, it seems that parallelism made it worse. So we have a parallel code, but it is not efficient. It is not efficient, my claim is, because we have too much synchronization. Too much is because we are synchronizing every single parallel iteration. Indeed, in worker.cc, this atomic construct is inside of the innermost loop. So we are synchronizing almost everything. we are not going to get any better performance on the Knight's Corner or Knight's Landing processor because this is not a good approach. So Knight's Corner gives us 3.3 times 10 to 7. And Knight's Corner, Knight's Landing, second generation Xeon Phi, gives us 1.7 times 10 to 7. So what do we do about it? Well, thankfully, this once again reminds us of the most common pattern in computing, and that is reduction. Because what's happening is we have a small array, hist, and we have many threads. And all threads are incrementing this array. Sometimes you're lucky and different threads increment different values. Other times you may have conflicts when different threads increment the same value. This is parallel reduction. We are modifying array hist, but all we do to it is we increment it. OpenMP has built-in support for reduction, and I've shown you in the integral calculation example how to deal with it. So let's just try it. Reduction for the operator plus on array hist. OpenMP should do everything behind the scenes that we need. So it allows us to remove the atomic. Well, let's see if it compiles at all, because, well, this is a different data type. Okay, we have a compilation error. Reduction variable cannot be const qualified. So hist is a const pointer to an integer, according to the C++ language. OpenMP thinks that we cannot have it as const. Okay, let's remove the const. Now, what do we do? Recompile. Still a compilation error, but a different one. No matching declaration for this reduction. And this already is a different problem. We did this trick for the numerical integration example. There, the reduction variable was a scalar. Now we are reducing into an array. And to make things even more complicated, hist is declared as a pointer-based array. So OpenMP tells us, sorry, I don't know how to do that. But there is actually a way to make it work. This way that I'm going to show you just now only became available in February 2017 because it was introduced in OpenMP 4.5, and it also took a few versions to get it propagated to the Intel compiler. So OpenMP 4.5 Plus supports reduction into arrays, but you have to specify a slice. Because this is a pointer-based array, the compiler doesn't know how much data is hiding behind it. But I can use array notation to specify a slice of this array that I'm reducing into. So I'm specifying 0, :m. It means m elements starting from element 0. And this is a different story. It compiles. It runs, and we will see how fast it runs in a second. So what we did is reduction plus hist 0, :m. So we are reducing on a particular slice of a pointer-based array, reducing into a particular slice. more room. Okay, now it's clean. So this command returns all the average performance, and the last three results are actually the performance of the last trial. So the CPU, the Ivy Bridge processor, now gives us 9.8 times 10 to 9 values per second. Knight's Corner 1.6 times 10 to 10. And Knight's Landing 2.3 times 10 to 10. So if you ignore this attempt that didn't go anywhere, the speed up that we get is a factor of more than 10 on the CPU, a factor of 100 on Knight's Corner, and more than a factor of 100 on Knight's Landing. The amount of the speed up actually is interesting. It is less than 24 on the Xeon. And that has to do with the fact that our application is partially compute bound. And I will show you in session 9 tomorrow how to improve the CPU performance by another factor of 2. So this is not the optimal CPU performance. At the same time, this is as fast as Xeon Phi can go. Long story short, this performance is not optimal because now we are memory bound, and this code is not NUMA friendly. So we will tweak NUMA locality in the next session. Okay, so we did that, and I think this is an illustration of what you do when you have too much synchronization. Basically, you need to look for a more optimal algorithm that minimizes synchronization. The reduction pattern behind the scenes, as you know, uses thread private variables to reduce into the common counter. I would like to stick with this exercise for a little longer because I want to illustrate another issue that can occur if you have advanced goals for your thread private data. So here is the performance result for the record, and we are moving on to the next issue. The next issue that I'm going to demonstrate is called false sharing. To understand false sharing, first you need to understand cache lines. Cache lines are minimal blocks of data that can be transferred between memory and caches. In Intel architecture, cache lines are exactly 64 bytes long, and it's not just an arbitrary 64 bytes. It is a block of 64 bytes aligned on a 64-byte boundary in memory. In simple words, when your application requests a single double precision value, what's going to happen is you will get this value from memory or from a cache, but together with this value, you will also get 7 of its neighbors that live in the same cache line. If you request one single precision number, you will get this number, and you will also get 15 of its neighbors living in the same cache line. This is, in fact, parallelism in memory architecture. And memory is organized in this way so that good applications, applications that go with unit stride, automatically take advantage of this parallelism. You do one true memory access, and then you have 7 operations for free, because you're going to be reading this from registers or from the main memory, or you're going to load the entire cache line into a vector register. At the same time, because cache line granularity of memory access is hardwired, sometimes it can backfire. And it will backfire in the histogram calculation if we slightly change the algorithm. So see how it would backfire. It would backfire if you have false sharing. False sharing is a situation that occurs when 2 threads or more access the same cache line, and at least one of these accesses is for writing. If you just change cache line to memory address, then you will have the definition of a data race. A data race is when 2 or more threads access the same address and at least one thread is writing. This time, it's not the same address, it's the same cache line. So even though it sounds similar, it is a very different effect, because when false sharing occurs, you don't get any inconsistency in your application. You don't get incorrect results. Your results are still correct, but your application is inexplicably slow. So this thread is writing this element, that thread is writing that element. They are different memory addresses, but they are in the same cache line. This will slow down the application. Why? It will slow down the application because caches in Intel architecture are coherent. They have a coherency protocol, which is supposed to make sure that at any time the view of the memory in any core is accurate. The cache coherency protocol that Intel architecture uses will lock this cache line. It will mark it as dirty when this thread goes in and modifies a value. And then these modifications will have to be synchronized with all other cores. And while the synchronization occurs, thread 1 will have to wait. So this is implicit synchronization. And it doesn't cause incorrect results, it only makes your application slower. Let's see when it might occur. It might occur if instead of using the clause, we tried to use thread private variables. And the worst scenario is when we use the thread private variables in this format. We declare one massive container that will contain compartments for different threads. So this hist.thr is a container containing as many small arrays as there are threads. So each thread gets its own memory space, but it is so closely packed that you get false sharing. Our histogram is very small. It only has 5 elements. 5 elements amount to 20 bytes. Cache lines are 64 bytes long. So in every cache line in our new organization, you have pieces of 4 histogram containers. And there will be no data races. Thread 0 is only going to write into its own container. Thread 1 is only going to write into its own container, and so on. But because these containers are so closely packed, you are going to have false sharing, because caches will have to keep maintaining coherency, and as caches maintain coherency, cache lines are marked dirty, and threads have to wait. As you can see from the next diagram, the solution to false sharing is padding. And Padding means that you will insert some unused space between the domain of every thread. With padding, you will have the container of one thread in one cache line, the container of another thread in another cache line, and in this way you should not have false sharing. By the way, when you do this, you should also worry about alignment, because padding by 64 bytes will only guarantee that you're not sharing a cache line if the initial container began on a 64-byte boundary. If it began like this, if it was split between two cache lines, so if one container was placed like this, another container like that, you still have false sharing. So you need padding plus alignment. Padding is easy in this organization. You just need to change the inner dimension of your array. Hopefully you now understand the theory behind false sharing. Let's see how it occurs in practice. So I have this reduction clause. It does what I need. But there are cases when instead of the reduction clause, you might want to use thread private variables. I will first implement it, and then I will explain what these cases are. So I will create hist global, which is going to be a two-dimensional array containing integers. The outer dimension, which in C is the first dimension, is n threads. The inner dimension is m. Here, n threads is the number of threads in OpenMP. In order to use it, I have to remember to include the header file for OpenMP. What do I do with this hist global? What I do is, inside of every thread, I go to my local, to my own memory address, and I only work with that memory address. So there's a recipe for that. I'm going to first turn this into two pragmas. Pragma OMP parallel with all the private clauses goes here, and Pragma OMP 4 goes there. This is just so that I can insert some code before the loop and after the loop. It is convenient because I will get to query my thread ID, different threads will receive different values here. Thread 0 will get 0, thread 1 will get 1, and so on. And then this. Hist private is scratch space for current thread. What I'm going to do with hist private is I'm going to use it when I'm doing the increment. It used to be a data race when I just had hist. Now it's no longer a data race because I'm using thread private storage. Well, if I do that, I've never touched the original container, and you probably remember this pattern from the integral calculation. I have to now do reduction. So here, I am outside of the for loop, but still inside the parallel region. So what I'm going to do is hist of C, I will increment it by hist private of C, where C runs from 0 to M. This is my reduction. So I create a big container, then each thread gets its own scratch space. Then I write my main loop. This is where most of the time is spent. And I'm going to record the age distribution, not in the global array, but in the thread private memory. At the end, I end up with a bunch of partial sums. And here I'm aggregating all the partial sums in the common container. Well, if I stop here, I will definitely get problems with results because this is a data race. Well, thankfully, there's not many operations here. I will only do 5 additions for every thread, and I have something like 200 threads, so 1,000 events. Compared to, so I can actually afford to go and put Pragma, Mutex, Pragma OMP Atomic to protect this right. This will guarantee that my results are correct at the cost of slowing down my application a little bit. That estimate that I gave you, 1,000 synchronization events, is just to estimate how much I'm going to be slowed down. Remember, when we put Pragma OMP Atomic here, we were synchronizing every single iteration, and there's this many iterations. N in our problem is 100 million. So we used to have 100 million synchronization events. By using these thread private variables, we went down to 1,000 synchronization events, so not too much synchronization. Okay, this is the correct code. Let me run it. And while it runs, as promised, I will explain why somebody might want to do this. This code is actually equivalent in terms of performance and correctness, equivalent to the reduction clause. It is, of course, much more complicated, but there may be 2 reasons why you might want to do this. First reason is when your operator or data type is not supported for built-in reduction. For example, if you're reducing into a custom object, OpenMP may not know how to conveniently replicate this object in memory. If you're reducing with an operator that's not supported by OpenMP, for example, something like top K or string concatenation, OpenMP will not know what to do with this. So this is when you might want to go this route. The second reason why you might want to go this route is when you want your thread private data outside of the parallel loop. As you can see, that container, hist global, is declared outside of the parallel loop. So when we exit the parallel loop, all the partial sums are still in memory. And that can be very convenient. For example, maybe your application wants to run some kind of advanced reduction algorithm. And you may want to run from a different function. Well, no problem. You can take this and you can pass it to a different function, so you retained a lot of the information from your parallel run. Maybe you want to analyze load imbalance, and then you want to parse this array in a subsequent calculation. It is not possible when you use the reduction clause, but it is possible with the thread private container. Okay, so I think I've made a claim that it should be the same in terms of correctness. Well, let's see if I was right. Oh, did not compile. Thread ID, I should have put a capital D. Okay, the last three results are obtained in this last run. You can actually analyze the files and you will see that there is no problem with correctness. But performance is actually disappointing. 1.0 times 10 to 9, 1.2 times 10 to 9, 3.6 times 10 to 9. So we seem to have done the same procedure that the previous algorithm was using, but our performance went down by as much as an order of magnitude. Of course, from the explanation in the theory, we know why that is. This is a very densely packed array. M is the inner dimension. It is only 5 elements long, so we have scratch spaces for different threads very close to each other. And because you fetch memory in increments of cache lines, every time this thread accesses one of the elements, all the other threads have to wait. All the other threads that share this cache line. In the lecture, in the slides, we also saw that if we separate containers a little bit, we should be able to avoid false sharing. You can do this by just changing the inner dimension. Let's change it to 16. 16 integers is 64 bytes, exactly equal to a cache line. Just to avoid accidents with splitting a cache line, I will declare that this array is aligned on 64 bytes. So I didn't change the code, I only changed the data container. So now the last three performance values are these. Can probably make it a little narrower. So the CPU now gives us 2.6 times 10 to 9. Knight's Corner gives us 1.5 times 10 to 10. Knight's Landing 1.3 times 10 to 10. Performance went up, but not as much as we were hoping. Well, on KNC, we almost recovered performance, 1.6, 1.55. But on Knight's Landing, the reduction clause actually worked better. Well, not all is lost. In fact, I can try and increase the padding a little bit. So from 64 bytes, let's bump it to twice that much. So I will change 16 to 32. Resubmitting. Well, now we get 6.2 times 10 to 9, 1.5 times 10 to 10, 1.5 times 10 to 10. You can see that performance is recovering on the CPU and on Night Landing. I actually did this experiment thoroughly, and I padded to 64 bytes, 128, and 256. So parallel code gave me this, and I was able to reproduce the same performance with the global container that persists across parallel region, but I had to pad to 4 cache lines. Particularly on the Xeon, which is green, and on the Xeon Phi, which is pink, red. The first generation Xeon Phi Knight's Corner didn't really care. It stayed flat as soon as we padded to 1 cache line. So there's actually another effect that you need to be aware of this to explain this, and that effect is prefetching. So it turns out that memory access is parallelized even further in advanced processors. So that when your code reads just one floating point number or 1 byte from memory, memory gives it the entire 64-byte cache line. But there is also a hardware prefetcher sitting on the memory controller or in the cache and monitoring this kind of traffic. And when it sees that this cache line was sent to the core, it says, oh, how about I send the next couple of cache lines to the core so that data is there before the core even needs it. And this is a good idea. If my core is doing unistride access to memory, then the data will get to it before it even asks for it. But in this case, when we have a parallel region where threads are bombarding nearby memory regions, that backfires because this cache line may actually belong to a different thread, and once again, I'm stuck with the cache coherency protocol. Well, this is padding to avoid false sharing. Before I switch to the next slide, I want to quickly show you how to do a solution that's alternative to padding. If instead of this massive container, and instead of finding a place in this massive container, I just declared hist private here, I will not have false sharing. Let me first show it to you and then explain. So that's the results with that alternative solution. And these results are just as good as the results that we first got when we parallelized the code with the reduction clause. They are printed in a different order, but you get the idea. So this is so see what we did in the last step. We removed the global variable. We removed the lookup in that global container, and instead we just declare hist private inside the parallel region. It works optimally. Why is that? That is because each thread will run this line. And because this line allocates a small array on the stack, each thread will automatically get this array on its stack. Each thread in OpenMP gets its own stack space. By default, it is 64 megabytes in size. And when your containers for different threads are separated by 64 megabytes, you are absolutely safe from false sharing. So this is easy, but of course it has the drawback that the data in these containers does not survive, does not persist outside of the parallel region. So if I wanted to do this kind of processing that I discussed earlier, maybe a custom reduction pattern or load balance analysis, that is not going to work. And instead you should go this route, but you have to remember to pad the scratch space for each thread. Well, if you have questions regarding this last demonstration or the previous one, feel free to ask them in the chat. We are near the top of the hour, so it is a good time to take a break. After the break, we will resume, and I will make two more demonstrations. I will demonstrate the common problem of insufficient parallelism and the common problem of load imbalance. For now, 5-minute break. For questions, please visit the chat. Talk to you in 5 minutes. All right, we can move on. And as promised, I will give you two more hands-on demonstrations of common problems in multi-threaded applications. The histogram calculation has served us well. We used it to do vectorization, multi-threading, and play with false sharing. But now it's time to put it to rest and move on to a different microkernel. We are going to talk about insufficient parallelism. And insufficient parallelism is a situation that occurs when there are not enough iterations or parallel quark items exposed to the parallel loop in OpenMP. This is a screenshot from a performance analysis tool, vTune, that demonstrates insufficient parallelism. On the x-axis is time. On the y-axis, you see several bands. So these bands are timelines of different threads. Brown color is good. It means that the thread was doing useful work. Orange color is bad. It means that the thread was spinning or idling and not doing anything useful. We see very severe load imbalance where only 4 threads are working and everybody else is doing nothing. This situation occurs in this microkernel. You can think of this microkernel as a prototype of a stencil operation, but really we are talking about the parallel pattern, and I'm referring to a large class of problems where this parallel pattern can occur. The problem we're solving is this calculation. We have a matrix Mij, and we want to sum the elements in all columns of row I and return them as the I component of the resulting vector. The twist is that M is small, but N is large. So the matrix has a very awkward shape. It is very short, but very wide. So that's my matrix. My goal, let me label it. So, one more row, sorry. So M is 4, but N is very large, something in the millions or hundreds of millions. My goal is to take this element plus that, plus that, plus that, and the sum of all these elements is going to be placed here. The sum of all these elements is going to be placed here, and so on. The way that the matrix is laid out looks very conducive to parallelism on Intel architecture. Well, this is the code for the calculation. If you ignore the directives, we have a loop iterating in I from 0 to 4. Here I set up a running sum, go through all the columns, increment the running sum, and write out the result. It is conducive to Intel architecture because the inner loop is ready for vectorization. J gives me unit stride to matrix M. What it means is that when J is incremented by 1, I move to the next element in matrix M. That's good. And definitely there is data parallelism because I'm just adding numbers together. This is vector reduction. Intel compilers know how to deal with it. The outer loop is also very good because if I parallelize this loop, different values of I will go to different threads. That's good. And different threads will compute, they will read different data, and they will write different data. Well, you can say that this could be false sharing, but it really isn't. It's so few memory accesses here that you can ignore false sharing in this case. Of course, you can see the problem. When you parallelize on these two levels, you will not have enough parallelism for threads. You have only 4 iterations to distribute across threads. So you will have at most 4 threads working. If you have a dual core or a quad core CPU, that's fine, but if you have a CPU like Xeon Phi with 64 cores and 4-way hyperthreading, this is not enough. So we are going to try and resolve this problem. You may look at this problem and think that, well, this is very contrived. Who has asymmetry like that in their applications? And I admit that the numbers here are chosen for dramatic effect, so that the effect of optimization is very clear. At the same time, even if M is in the tens or even in the hundreds, you may be underemploying your cores by a sufficient amount to look for optimization. Plus, I will promise that in session 10, when I discuss loop tiling, we will see a case where we have a more or less, well, a less asymmetric matrix, and then we apply a technique called loop tiling, which thins out the iteration space so much that instead of many iterations, now we have very few. So this kind of situation, too few iterations in the outer loop, may occur even if the natural matrix sizes in your problem are not so asymmetric. Okay, well, let's actually test it on a cluster, convince ourselves that it is not working very well, and then we are going to try and optimize it. On the cluster, you can go to lab 405 and also open worker.cc. I'm compiling, submitting to the queue, and as usual, first we will record the baseline performance. As I type, feel free to take a look at the code to understand what's happening better. Okay, so here are performance results. The units in which I measure performance in this case are gigabytes per second. Why is that? Clearly, most of the time I will be reading the matrix M from memory. Because in addition to this reading, I just have the increment. And one arithmetic operation per number read from memory is really nothing. We will see in session 10, we will see how this is, there's really a huge factor between how many operations your core can perform and how much data your memory can deliver per second. So I'm measuring the performance in gigabytes per second so that we can compare our performance to something like the memory bandwidth benchmark. The original code on Xeon gives us 46 gigabytes per second. On Xeon Phi, it gives us 10. And on Knights Landing, it gives us 46 gigabytes per second. I want to point out that for Knights Landing, I'm using the little trick that I mentioned in session 1. I'm going to revisit this trick in session 10. I'm using the high bandwidth memory to run this application. So even with high bandwidth memory, I'm not doing as well as the Xeon. These numbers that I've shown here are tests of the stream benchmark, and specifically for the triad test. I will talk more about the stream benchmark in session 10, but treat these numbers as the target. This is the most that we can expect from each of these platforms. So why are we not getting good performance? Well, clearly because we don't have enough parallelism. How do we resolve it? You probably have had time to think about it, so if you have suggestions, please feel free to post them in the chat. Usually, there's a few routes that people suggest. And yeah, the route that most people see is very obvious. M is small. N is large. So why don't we parallelize the inner loop? It's very easy. Take this, move it here. Well, sum is shared across threads, so I will have to do reduction plus on variable sum. But other than that, it's a done deal. This is not a bad solution. I will explain soon that this is not the most flexible solution, but I have to admit it works pretty well. So parallel inner loop. Let me make more space. So with parallel inner loop, are we done? With the parallel inner loop, we get way better results. The CPU gives us still 45 gigabytes per second. Knights Corner gives us 167 gigabytes per second. Knights Landing gives us 328 gigabytes per second. This is not bad at all, but my claim is that this is not optimal. It is not optimal in general to have parallel loops inside of some other loops. For two reasons. One is that we don't expose all of the parallelism, which is bad. And the second reason, we have to start and stop parallel regions and loops m times. So if m is small, of course, this is not a big deal. But if m is a little bit larger, for example, it is in the tens, then it can incur a significant overhead. And at the same time, m of order a few tens is not enough to occupy the entire chip. So I will declare it as an almost satisfactory solution, but I want to roll it back. I want, in general, to keep parallelization across threads as far out in the algorithm as possible. And I will try to use a different functionality, a functionality called loop collapse. So I'm asking for loop collapse. Let me explain what I'm trying to do. In OpenMP, you can parallelize the iterations not of one, but of two nested loops across threads. To do that, you just put the collapse clause and indicate how many levels of loop nesting you wish to collapse. What will happen is OpenMP will parallelize not this iteration space, but it will parallelize across the Cartesian product of these two iteration spaces. There's no complex math in it. You can rewrite the same code like this. Just write one loop that has m times n iterations, and parallelize this across threads, and then assign different, with every value of c, increment j, but to no more than n, and then every n iterations increment I. So this is equivalent. But OpenMP just has a very elegant way of doing that. By doing loop collapse, looks like I'm going to be exposing all of the parallelism, and regardless of the values of m and n, I should have a good enough calculation. Well, does it work? It doesn't work. Reduction sum is no longer applicable because sum is declared inside. Another problem. Parallel loops with collapse must be perfectly nested, and they are not. Perfectly nested means that there should be absolutely no code between the I loop and the J loop, but there is this private variable declaration. So can we get rid of it? Let's try. So if we do that, sum, what do we do with sum? We can't move it outside. How about we do just directly s of I plus equals that. And we will, because s is relatively small, we will do reduction for the operator plus on the variable s. And because it is an array, I have to specify the slice. So this is what we learned in the histogram calculation. Reduction. I think it should work, because now we expose all of the parallelism that we have, and regardless of m and n, I should have enough iterations. Just one thing, in this lab, just the way that we wrote it, s comes in uninitialized. So I want to initialize s here. It wasn't necessary before, but now it is. Well, that should work. Let's see. OpenMP agreed with the syntax. I know that this is a data race, but this is a trivial case of a data race. This is reduction, so I'm using the reduction clause, and my code is now running. So I collapsed two loops. Let me see what it gets me. Oh, you know what? I typed make. I forgot to do the queue thing. Okay, now it's gone to the queue. Okay, almost done. Okay, the last three results is what we're getting now. And they don't look so good. Well, actually, on the CPU, 55 gigabytes per second is quite nice, but KNC only 8 gigabytes per second, KNL only 28 gigabytes per second. So what happened? The clue to what happened is in the optimization file. This is a very useful tool. If we look at the optimization file, now we need to look for loops, for the loop in line 6, because this is how the compiler treats loops with directives. They begin on the same line where the directive is. So it was parallelized, that's good. The loop in line 3 was vectorized. And the loop in line 6 was vectorized. This is strange. You know what? I've done this problem in a slightly different format in the past. So maybe the reduction was vectorized, but apparently not the sum itself. Do I demonstrate it differently? Just a quick test. I know that what happened is loop collapse killed vectorization. Yes, so in fact, if I remove the reduction clause, I get a remark. Loop was not vectorized because there's flow dependence. So the fact that we saw loop was vectorized was just because I had the reduction clause, and I think it vectorized reduction rather than the calculation. So I guess I can comfortably claim, I'm pretty confident in this, that what happened with loop collapse is we killed vectorization. OpenMP and the compiler were not able to agree with each other what belongs to threads and what belongs to vectors. This is actually a perfect case for a technique that earlier I said can help vectorization to coexist with threading. That technique is strip mining. So we do want to expose as much parallelism as possible, but we still want to retain some parallelism for vectors inside of the parallel loops. Because, well, that's the nature of the Intel architecture. You have multiple cores with vector instructions inside. So you want to have enough parallelism for cores, but still enough parallelism for vectors that work inside of cores. So strip mining should help by exposing vectorization opportunities. Strip mining is not difficult here. I will just go in JJ from 0 to n with a certain stride. And then in J, I will go from JJ to JJ plus stride. This is the same sequence of operations. Well, as long as n is a multiple of stride, but written in a different way. Now, when I collapse these two loops, I still leave that one for vectorization. I just have to choose the stride. And when you do strip mining, you need to be aware that the stride is always a tuning parameter. In some cases, the optimal values of stride will be comparable to the vector width. In other cases, the optimal values of stride will be comparable to the size of the level 1 cache. This is actually the second case. And you can experiment if you wish, but I will just record what I know. Something like 10,000 is actually a good value for this code. When I compile, I hope that the optimization report will tell me that the loop is now vectorized. The loop that I'm interested in is in line 12. So peeled for vectorization, multi-versioned, version 1 vectorized, and then version 2 not vectorizable loop instance. This has to do with pointer aliasing. If M and S are aliased, it is not safe to vectorize, so the compiler will do a check. If it checks out, the compiler will not hold it against me and vectorize. If during the check the compiler finds that M and S are aliased, they are pointing to the same memory location or to overlapping memory locations, the compiler will, the code will fall back to serial execution. So I'm submitting it to the queue. And while it's running, here is our log. So what we did is strip mining. So what happened after strip mining? So these are the last performance values, and they look pretty good. 89 gigabytes per second on the CPU, 192 gigabytes per second on Xeon Phi, and 333 gigabytes per second on Knights Landing. And I have to admit that this is also not an ideal code. It assumes that M times N is much greater than 1000. It also assumes that M times N is that N is a multiple of 1000, 10,000. These are the two assumptions that this code makes. But it will work for any relationship between M and N. If M is large, if M is small, it will work just as well. So that's because it exposes all of the parallelism. A quick word on why we got more than I quoted here, and why we got less than we quoted here. These numbers are for the triad test. In the triad test, you do A of I equal to B of I plus alpha times C of I. So it's three operations: add, multiply, and copy. What we are doing is actually a read test. There is no read test in the stream benchmark, but when you just read, memory behaves slightly differently. Specifically on the Xeon, it works slightly better than the triad, and so all on Xeon Phi the same. On second generation Xeon Phi, it works slightly slower than the triad test. But this is an illustration how loop collapse and strip mining allowed us to move parallelism from vectors to threads. And this way we resolved the problem of insufficient parallelism. Of course, I demonstrated a very limited example, but you can generalize it. If you have enough parallelism in your program overall, but it is expressed at the wrong level, you might need to move parallelism from MPI to threads, from threads to MPI, from threads to vectors, from vectors to threads. And usually, strip mining, it is centered around strip mining, and expanding the iteration space is centered around loop collapse. If you have more questions about this example, we have the chat, and you can ask questions there. My slides show the results. Yeah, this is what I did when I definitely saw that there's no vectorization. Remember I said that I did it differently loop collapse kills vectorization. This is what I did. I used thread private variables to implement parallel reduction. Screenshot in VTune looks better. All threads are working, all timelines are brown, and here is the performance plot. In the case of Xeon Phi, on this performance plot, I made two tests, one in the on-platform memory and the other in the high bandwidth memory. Today, we are talking about the optimization of multi-threaded applications, focusing on common issues. And the last common issue out of 4 that I wanted to illustrate today is load imbalance. In session 4, we talked about loop scheduling modes in OpenMP. It is very easy to change the scheduling mode. So if you have Pragma, OMP, parallel 4, you can add the clause schedule, and in parentheses put, for example, static, comma 5, and this will be your scheduling mode. There's other ways to do this. I will show it in the next slide. But there are 3 methods that you have access to: static, dynamic, and guided. Static is a low overhead and no balancing method. With the static scheduling mode, OpenMP assigns iterations to threads before the loop even begins. By default, it assigns approximately equal contiguous chunks of iterations to different threads. If you set a grain size, a chunk size, OpenMP will assign this many iterations to every thread, and then it will loop over and continue until all iterations are assigned. But the key here is that at runtime, the mapping of iterations to threads does not change. This can lead to load imbalance, because one thread may be working while all other threads are idling because they're done with their work. If you want to avoid load balance, you may want to play with the dynamic mode. The dynamic scheduling mode gives one iteration to every thread. When this thread is done, it receives the next iteration. Another thread is done, it receives the next iteration, and so on. So at runtime, you decide which iterations go to what thread. This is a high overhead and high balance method. If the overhead of this scheduling every time is too high, then you can play with the scheduling chunk size. With the dynamic mode, the chunk size is an integer indicating how many iterations to assign in every scheduling event. So instead of one iteration, OpenMP in this case will assign 2 iterations in every scheduling event. This will reduce the overhead by a factor of 2. By tuning the chunk size, you can find a trade-off between load imbalance and scheduling overhead. If the chunk size is small, you have good balance but high overhead. If the chunk size is large, you may not have enough chunks to populate all threads, so you have poor load balance but low overhead. The guided mode tries to expand the range in which you get the sweet spot. And it does so by first distributing large chunks of iterations, and as iterations go on, chunks become smaller and smaller. In this case, the chunk size is the minimal chunk size towards the end of the calculation. To tune scheduling, you can either hard code the scheduling mode in the code, or you can defer the setting of scheduling to the runtime. Just set schedule runtime, and then at runtime, your code will be sensitive to the environment variable OMP schedule. Whatever you set it to is what your code is going to use. Plus, there is also compiler argument. It reads, I think, par schedule. If you set multiple methods, then this is the highest priority, this is the second priority, and this is the third priority, if I'm not mistaken. I will demonstrate a quick workload to, well, to have a hands-on exercise for that. The workload is going to exercise an iterative Jacobi solver. The solver solves the system of equations ax equals b, and it solves them iteratively. X prime is equal to x plus x prime I plus b minus bi minus c divided by mii, where c is mij xj. Basically, you start with the initial guess for your solution, and then you crunch this iteration many, many times until you find that your accuracy, your residuals, are good enough. Because you have a while loop and you don't know when it will end, you are sensitive. Because you don't know when the loop will end, the runtime of this function depends on the quality of the initial guess, it depends on the required accuracy, and it depends on the condition number of the matrix. As a consequence, we can observe load imbalance with this calculation if we distribute different calls to this function to different threads. Load imbalance in vtune will look like this. What you're looking at is the thread concurrency histogram. On the x-axis, you have how many cores the code is using. On the y-axis, you have how much time the code was using this many cores. The bad aspect of this diagram is that it is smeared all over the spectrum. So sometimes the code was using all threads. Then as load balance fell apart, the code was using effectively fewer and fewer threads. And there were even cases when the code was using just 1 or 2 threads out of 48 available. In the timeline, it will look like this. Brown with gaps of orange. You see this repeating pattern here because, in fact, this is just several instances of this loop. I run this parallel loop over and over and over just to accumulate statistics. So this is the beginning of the loop, this is the end of the loop, and these are the unfortunate iterations that take more time than everybody else. To resolve load balance, you have to tune the scheduling mode. And when load balance is good, thread concurrency histogram should be concentrated in the ideal range, and the timeline should be all brown. I will demonstrate how it works, and then I will show you the plot, and we will discuss it for a minute. We are going to lab 406. And there's not much to look at in the code. This is the iterative solver. We are not going to change anything in the code. We're just going to look at main.cc and see how it works. We have multiple loops. One loop uses default scheduling. Another loop uses static scheduling. One more uses static scheduling with a different chunk size, and so on. Then there's loops that use dynamic scheduling, guided, and all of these results are printed out on the screen. So we'll just compile and run and see what we get. It takes a few seconds, and we will get the numbers. Okay, so Knights Landing results are out first. And this is what we see. So the code starts with the default mode, and the best it gets is 0.145 seconds. So lower is better. Then static scheduling with a chunk size of 1 gives us 79 milliseconds, 79, and then it starts going down. The dynamic mode gives us at best 0.75, slightly better, and guided mode gives us also 0.74. If you plot this, you will see two trends. One trend is in the dynamic mode, that the runtime lowers better. Looks like this. This is dynamic mode with different chunk sizes. So if the chunk size is too small, on this side we have suboptimal code because we have too much synchronization, too much scheduling. If the chunk size is too large, we are there because we have insufficient load balance, poor load balance. And there is a sweet spot here where the time is lowest, so performance is greatest. The other trend that you can see is this one. This is different chunk sizes for the guided mode. The guided mode also has the problem that at the large chunk size, towards large chunk sizes, you have poor load balance. But for small chunk sizes, the nature of the guided mode reduces the overhead, and you basically have more room for error when you're estimating the optimal chunk size. The static mode didn't work very well in this case, but we will see in session number 9 tomorrow, when we talk about NUMA architecture, that static is sometimes the most NUMA-friendly way to schedule loops, so it definitely has its place in OpenMP and in performance optimization. You can ask questions about this presentation as I speak or as we finish, but I would like to wrap up the session with a review. We talked about common problems in multithreading. Too much synchronization. Well, you need synchronization to resolve data races, but you must move out murexes out of the innermost loops, maybe with the help of parallel reduction. False sharing. It occurs when threads write data that is packed too closely. You can resolve it with padding. If you have insufficient parallelism, the key approach is loop collapse, and if it kills vectorization, use strip mining. And when you have load imbalance, you can play with the scheduling mode, and you need to find a trade-off between load balance and scheduling overhead. Multithreading is difficult. We already had one session on how to express parallelism. Here is one session on how to work around common problems. We have one more session on the optimization of multi-threaded applications tomorrow, and we will talk about the connection between threads and memory. So optimization of multi-threaded applications from the memory aspect. We will talk about thread affinity, NUMA locality, nested parallelism, and its relationship to threads and memory. Thank you for joining us today. I hope this was a useful session, and I look forward to seeing everybody again tomorrow, same time for session 9. Have a good rest of the day. Goodbye.